Okay, good afternoon and welcome to today's class. If somebody can confirm that you can see my screen and that I'm audible.
Yes, sir, we can see the screen and your audio also.
Okay, so we start off this lecture by going over some of the things that we did towards the end of the class, and we were actually started discussing the state of charge. And in order to discuss about state of charge, we needed to define some uh, parameters or some variables. And one of them was, of course, what is a fully charged cell? So it is a cell which has been charged to the upper cutoff voltage as well as then continued to be charged at the upper cutoff voltage till the current falls to very small values. Okay, and what those small values are quantified here. Similarly, a fully discharged cell is a cell which has been discharged at constant current to lower cutoff voltage limit and then continued to be discharged at constant voltage at lower cutoff voltage value till the current falls down to very small value. Okay. After that, we define what is the total capacity of cell, what is the discharge capacity of cell, and what is the nominal capacity of the cell. And then we went on to define what is SOC, which was Q residual divided by the charge capacity of the cell, okay, or total capacity of the cell. And then we define DOD, which is complementary to SOC. It is 100 minus SOC or 1 minus SOC, depending upon whether SOC is expressed as percentage or as fraction. And then we add some simple problems. And then we define state of health, which is essentially a quantitative parameter, again in percentage term, defining or determining or quantifying what is the maximum amount of charge that a cell can hold now as compared to the maximum value when the cell was new. Okay, so this is something that we did at the end of the class. Okay, what we will do in this class is to look at the estimation of SOC. Okay, and there are good reasons why we should be estimating SOC because if the cell is an energy source, the application would want to know how much energy is left. Okay, so amount of charge is a proxy for how much energy is left. Now, estimation of SOC for a cell which is operating is different from laboratory setting. Okay, you cannot open the cell and you cannot do very complicated or very involved analytical measurements. What you can measure based on that, there are categories of estimation methods. Okay, so there are methods that primarily rely on voltage measurements to then estimate what is the state of charge. So measure the terminal voltages of the cell and then from that decipher what would be the state of charge. Or methods which do not rely on voltage but rely on measuring the current flowing through the cell and then from those measurements decipher or estimate what is the state of charge of the cell. Then there are categories of method where both voltage and current measurements are used together. Along with usually these methods will require also or will use some model of the cell. Of course, the model is expected to be accurate. And if we can do it well, then it can estimate the SOC of the cell. Okay. Uh, okay. So one of the things that probably, where is that slide, which is not here, probably, did I remove it? Okay. One of the things uh, to be mindful of is that we not only have to estimate or the ideal condition would be that we are able to estimate the SOC from these measurements, voltage and current, but we are also able to gauge whatever SOC we have estimated using our method, what is the kind of accuracy associated with those estimates. Okay, so that also needs to be kept in mind. Okay. So the first class of method, which is the voltage-based method, the SOC estimation, essentially, if you go back to our discussion on the equivalent circuit model for cells, wherein the idea was to uh, get cell voltage and also get how it is related to current. Okay, so if you recall those discussion, the terminal voltage of cell at any time t depends on what is the OCV, and that OCV depends on the state of charge and the temperature at that time, minus the current flow multiplied by the equivalent series resistance, minus the voltage drop that occurs along the capacitor or the polarization element, minus the hysteresis. This we have not covered in this course, so let's forget about this. Okay, just so that you can recall it, let me go back to that slide. Okay, so okay, fine. So when we were doing this uh, equivalent circuit model, this is the model that we said is more commonly used. Okay, in embedded system. So you have an open circuit element. You have a single polarization element, which is a parallel combination of a resistor and a capacitor, and then equivalent series resistance. Okay, an ohmic resistance, and you get an equation that relates the terminal voltage to OCV, the current flowing, the equivalent series resistance, and the voltage drop across the polarization element. If we include a hysteresis element also in the model, then we will have that H1. Okay. So for our course, let's forget about that. Okay. Yeah. So that is what. So that is our understanding of a cell, or the simple understanding for a cell. So essentially, the idea is that this equation on the left hand side is voltage. On the right hand side is OCV along with other terms. And since these two are related, can I invert the equation, take OCV on the left-hand side, bring terminal voltage here, and then of course keep every other element. So from the voltage measurements and also accounting for other things, I can get OCV. Okay. Now, of course, we see immediately that this equation, in order to get OCV, you will also require not only voltage but the current. Okay. For the moment, assume or think of situations where the cell is at rest, that is, no current is being drawn. Okay. And also ignore the hysteresis. So this element is zero. This element is zero. Also, what happens is this VC1 will also drop down to zero if we have waited for sufficient time after there is the current flow through the cell becomes zero. Okay, so all these three elements will go to zero. If we are talking about cell which has been at rest for some time, uh, which means that current has stopped for some time. Okay, then we have simple relation that the terminal voltage is basically OCV, and OCV depends on the state of charge and the temperature. Okay, if you recall, this was the first model that we developed, okay, or that we started to discuss when we started talking uh, about the equivalent circuit model. So this was the slide we started with: cell, OCV, cell at rest, and then we said that the equivalent circuit model is very simple like this. Okay, so we are basically going back there. Of course, now with an objective to make use of this OCV measurements to get the swell voltage. So this is the graph to remind you that this is something that we considered previously. But when we considered previously, what we had was that we wanted to calculate voltage from the OCV measurements. Okay, a terminal voltage. We wanted to ultimately get terminal voltage by doing OCV measurements. Uh, Here, what we want to do is making use of this OCV measurement or whatever is terminal voltage. I want to get this Z, the state of charge. So here, what has happened is SOC previous discussion when we were talking about the equivalent circuit model, SOC was independent variable that was on the x-axis, and OCV was the dependent variable, so it was on the y-axis. And if we look the curve like this, it looks pretty straightforward to say that once I know the value of SOC, I can get OCV. But now the problem is inverse. I know the value of OCV, or at least some voltage which is very close to OCV. And from that, I want to get the SOC. So I have to invert the graph. Okay. The right hand side is inverting the graph, which means that now open circuit voltage is on the x-axis and SOC is on the y-axis, the dependent. Okay. And immediately what you see is that the voltage is, if I look at this curve, there are variations at some regions of the voltage versus OCV, but there are regions and pretty large region in SOC space, okay, wherein there is very small change in the voltage or a significant change in SOC. Extreme situation is shown by this graph, the blue one here. But then you have similar kind of steep rises in SOC for very small change in the voltage. Okay. So that is going to present a problem when we use voltage measurements for SOC estimation. Just to show how it creates a problem, uh, is consider this. This is for LFP cell. So there are some values which are given here that for an LFP cell, OCV at 3.3 volt, which is around this value, okay, corresponds to something like 42%, assuming that this curve accurately depicts the SOC to OCV relationship. Okay. However, if the OCV changes by only 10 millivolts, which is 3.3 minus 0.01 volt, okay, the OCV, which will be somewhere here, the OCV drops down to about 32 volts. And if it increases by 0.01 volt, okay, the SOC will change to 66 percentage. Okay. Now, if we have very small current flowing through the cell, it is quite possible, or in fact will be always the case, that the cell voltage will change by about 0.01 volt from the OCV value. Okay. Or even if the cell had not rested for enough time, it is quite possible that the terminal voltage is about zero point zero 0.01 volt up, either above or below the OCV. And so that kinds of tells you what kind of inaccuracies we are going to get if we were to use OCV measurements to get the SOC estimate. Okay, unless we are sure that the cell is completely at rest, it is possible to reduce this error. But even if it is completely at rest, there will be some measurement errors associated with whatever measurement tool that we use for getting the voltage value. They will also introduce some errors here, which may be very large for LFP, would be non-negligible, although manageable, but non-negligible for other lithium-ion chemistry. Okay, so that's one thing that you should keep in mind or understand very clearly. Okay. Uh, then, so we cannot directly, so what this data shows us is that just using OCV or terminal measurement as proxy for OCV is going to give us a lot of problem in terms of SOC estimate. Okay, so if we go back to this equation and say that this is not good enough, especially when we flip the graph to represent the situation that voltage measurement is now independent variable and SOC is dependent, then we have to go back to this equation and see which one of the parameters is easily determinable. And we find that this is quite reasonably one can estimate. Okay, one can get current to to good accuracy, and R0 is pretty easy to estimate. Okay, so if we do that, then my equation will look like that the terminal voltage is OCV minus I times R0, which essentially says that OCV is the invert of this function, how OCV depends on state of charge and temperature. So invert this, but instead of using the voltage, use voltage plus I R0. Okay. If we use this, and people have done experiments on doing that, you get these kinds of a graph. Okay. What this kind of a graph is telling you is that if you have a highly dynamic current load, highly dynamic current load means current is changing very rapidly with time. Okay. For example, in a real, let's say you have an EV and and somebody is driving. Okay, so there may be opportunities for acceleration. There will be situation where you have to decelerate, apply the brake. Even when you are accelerating, you may be accelerating slowly and then fast. So those who have driven a vehicle will understand for how long, a very small amount of time you apply acceleration and then you wait. or you there is no other option but to wait and let the vehicle move with some speed, then you are forced to lower or again increase the speed. So usually in practice that is expected to be very dynamic. Even for mobile phone batteries, for example, the other user case, or laptop portable electronic devices, the load that is put on the energy source is highly dependent on what is the computational load that goes on inside the processor, and that may change depending upon what activity you are doing. Okay, so you may be watching something where the frames, let's say you are watching a video is a running of lot of frames at certain speed. So many times what will happen is a cluster of those frames which have to be changed on the screen have lot of similar elements. Okay, so if you watch a movie, for example, or any video, you will find that many instances the background remains practically the same, only in the foreground somebody is moving. Uh, then what happens is that the amount of energy that is required is less because a lot of other things are very similar. Okay, so when the frames come, not much changes on the screen except things which are a very small part of the screen which is changing. Sometimes there is a very rapid change in the screen. Okay, so all those will create different or highly dynamic current load. Every time you have this, the result becomes quite noisy. Okay, how noisy it becomes is given by this curve, okay, which is the blue curve is telling you the SOC estimation that you are going to get from this equation. And if you can see, it is all over the place. Okay, the true SOC is shown by the pink curve. Okay, so you can see how when you have dynamic loads, how the SOC estimation becomes very noisy as compared to the true SOC, which is still dynamic, but it is not so noisy. Okay, it also has uh, uh, a sawtooth-like profile, which is used deliberately to show you this thing. But then it is not so noisy as compared to the estimate using this equation. Okay. Now, of course, people who are familiar with these signal filtering, especially electrical engineering background, can tell you that every time you have signal which has noise, one can filter out the noise by having low pass filter. So you can apply, and low pass filter is again like a capacitor and resistor in series, which is applied. And what it will do is it will remove the high frequency noise, and you can decide beyond what frequency the things will not be noted. Okay. But the problem with doing this low pass filtering is that it introduces a time lag. What is meant by that is it will give you an SOC value at 100 second, something which was at, let's say, 95 or 90 seconds, because that is what is meant by time lag. Every time we do a filtering, it will introduce a time lag. So there are issues associated with voltage measurements. One, if you use only OCV, you will run into problems of lot of inaccuracies, uh, and there will be very small fraction of time when the this equation, that voltage is basically related only to OCV and no other thing, because that situation is when the current has been stopped and we have waited for sufficient time. Okay, those situations are very small fraction of time in any application. Okay, if we go to the next higher thing wherein I introduce a current, then the problem is that you create a lot of noise, especially when the current load is dynamic, okay, which is expected many times in usage of application. So these are the issues which are associated with voltage-based measurements or SOC estimation. Okay. If we talk about current-based measurements, so it is primarily using current to measure the SOC. Okay, before I go to this, any questions up to this point of time on voltage-based methods for estimation of SOC? No? Okay, so the next class of method is making use of current measurements to do an SOC estimation. Okay, and these methods are also, the jargon used is Coulomb counting. Okay, what is this method based on? It is based on the fact that the amount of charge is simply integral of the current over time. Okay. So the idea is that whatever is the change in SOC, remember that we start with change in SOC. So it's an updation method. If I know SOC at some instant of time, which I call time t is equal to 0, I don't know how I'm going to get the SOC at time t is equal to 0. But if I know SOC at time t is equal to 0, and I am required to calculate what is SOC at time t t is equal to delta t, then all that I have to do is to keep measuring the current between time t is equal to 0 up to time t is equal to delta t. And from there, I can calculate what is the amount of charge that has changed in the cell, and that change in the charge will be the current that is flowing multiplied times dt and integrated over t to t plus delta t. Okay, and divided by q. Somebody wants to say something? Is there a question? Okay. So what is inside the integral is the amount of charge which has flown out of battery or flown into the battery. Okay. And this we are calling it as IC. Okay. So inside a cell. Okay. Divided by Q. So this is the change in the charge of the cell. We divide by Q. Why? Because the SOC is defined as the charge of the battery by the total capacity. So this is the change in the charge divided by the capacity. So it will give you the delta SOC. Okay. But this assumes why we have another factor, which is eta. This is brought in to take care of the fact that not all of the current that we see actually goes into changing the charge stored in the battery. Okay, there are efficiencies associated with charging and discharging. So, for example, if the cell is being charged in this instant from in this interval from t to t plus delta t, then the amount of current that we see going into the cell, not all of it will go into charge storage. So that fraction which goes into charge storage is accounted by this factor eta. If there's a discharge and IC is the discharge current that we see, the cell has actually uh, uh, more amount of charge has come out from the electrode than what gets flown out in the outer circuit, which we can see. Okay, so that eta accounts for the efficiency or inefficiency of charging and discharging. Okay, so the term which is after this plus minus sign is the change in the SOC, which is what delta SOC is. And so my Coulomb counting method or current based method is simply the state of charge at time t plus delta t is equal to the state of charge at time t plus or updated with what is the change in the SOC in this time interval. Okay, so in principle wise, it's a very straightforward thing. Okay, uh, and in principle, the method is precise. Okay, Uh, so if we see that IC is the current that I can measure correctly, and eta is the efficiency that I know very to accuracy of 100%, then this method is 100% accurate. Okay, so that is what is said. In principle, the method is precise, but in practice, the relation which is actually applied is whatever is my estimate. So I've just put the cap on Z to indicate that this is the estimate. Earlier, there were no caps, so we are talking in terms of actual values. Okay, so that is in theory. This is what happens in practice. So estimate of the state of charge at time t plus delta t is equal to estimate of the state of charge at time t. And what is the updation? Plus minus depending upon whether I'm charging or discharging. What is the estimation of the efficiency? So you have cap over eta again. Then what is the estimation of the total capacity of the cell? So you have cap over here. And instead of true current going into the cell, I can only measure the current outside the cell. So what is the measured current? Okay, so remember that just notice the difference between the top and the next equation. There are all estimate and then you have IM instead of IC. So instead of knowing the true current going into the cell, we only know what is the current measured at where the my current measurement sensor is. It will be outside the cell. Okay. So, and since we have said that there is no way in this method to get uh, the state of charge at the beginning, okay, that is at the time t. Okay, so it's an updating method. So accuracy at time t plus delta t depends heavily on the accuracy at time t. Okay, what is the initial estimate? Okay, if this estimate is inaccurate, then of course your follow-up update will continue to be uh, uh, equally or uh, even worse in terms of accuracy than the initial estimate. Okay. So one of the big problem with this current updation method is if your initial estimate is inaccurate, there is no feedback mechanism to correct it. Okay. Now, knowing the true capacity of the cell and the true efficiencies of charging and discharging, usually not known, we only use estimate. So those are also going to contribute to the SOC estimation error. Okay. What are the errors that you get? So this is just some, I don't expect you to remember all of this deeply, but at least be aware of these. So this measured current actually consists of so many components. Okay. It is the true current that goes into the cell. There is some noise, which is always there in any physical process. There may be some bias, which is introduced because of the circuitry and measurements. And there is a non-linear element of uh, which adds on to the current, which comes from whatever electronic components you have in your current measuring sensor. Okay, and we don't go there. And then you have a self-discharge, all cells, even though the discharge will be rate of self-discharge is very small, but there will be some small amount of current that goes there. And there is some leakage current if the cell is short-circuited or if the connection into the cell is not proper, then you can have some leakage current through it. Okay. Maybe it was over discharge and there may be an internal leakage, or there could be a leakage due to faulty connection outside the cells. Okay, which may be very small current, but still could exist. Okay, so these are those things. Again, we will not go into that because we are not um actually doing we are doing principal course and not application. So I'll just speak about these. So remember, every time you have these components which are creating errors into your measurement or estimation, the errors have to be accounted for, or we should be aware of that they come or they bring in two implications. Okay. One implication is how much is my estimate away from the actual value. Okay. So that is what is has to be given by what is the mean of these. Okay. So if I look at this noise and nonlinear element, they're not constant values. Okay, they are varying with time. So when I'm measuring this IC over time period delta t from t to t plus delta t, none of these current is constant. Okay, they themselves are fluctuating. However, what happens is that if I take an average for I noise or I nonlinear, it has a zero mean value. Okay, so because of that, they are not going to affect the accuracy of the estimate. But what they will do is they will may increase the uncertainty of the estimate. Okay. So essentially, that's the point that okay, let me just work through this and then talk about what it means. Then you have bias current, self-discharge current, and leakage current. They have non-zero mean value. Okay. So they will increase both the error as well as the uncertainty associated with the measurement. Okay. So what is meant by these things is that if if your actual current value is, let me just move this a little bit. Let's say your actual, so we have this line which is kind of telling me whether currents are accurate or not. These are just telling me where the current values need to be. Okay. Or SOC is, where the SOC is. Okay. So let's say that the real value of SOC is here. This is the true value of SOC. Okay. Uh, when I'm doing an estimate, I don't know if these values are true or not. Then when I have to talk about the inaccuracies, okay, following things are there. One is that my method is inaccurate and it calculates the value here. So this is my estimate, okay, which means that the error accuracy of my measurement is this horizontal bar. The true value is here. My estimation method has done, has given me this value. And this is the inaccuracy, or this is uh, the error that I have gotten in my estimate. Okay, so that is what is determined by whether these current have a zero or a non-zero average value. Okay. However, remember that I neither know this value, the true SOC, because if I know the true SOC, I will not be able to, I am not required, or I do not have any need for this estimation method. So I do not know this blue vertical line. What it also means is that I don't know this horizontal line, which is the error. Why? Because this is difference between the distance between these 2 points, and I do not know one of the points. Okay, so therefore, not only when we get into this situation, we have, or there is another thing is whether the error is this amount, or it is this amount. Okay, or basically shift it here because at least I know the thing. Okay, or is it this amount? Okay, or is it this amount? Okay, even higher. Okay, so you also need to get an idea, but because we don't know what this line is. Okay, so essentially you are also going to have a distribution of error. Okay, you will have a distribution of error. Okay, something like this, a bell-shaped curve or something like this. And how big this bell-shaped curve is what is called as uncertainty of estimate. Okay, so these two errors are not going to increase the average value. They are not going to affect where how far your red line is from the blue line, but it will increase the uncertainty because you will not be able to tell whether your red line and blue line are just 1% away or 3% away. Actually, presence of these will increase from 1 to 3. Okay, the second type of errors, which are these three, are also going to shift this distance. So they are going to make the estimate more accurate, and they are also going to enlarge this envelope of error. Okay, that is what is meant by this. If you don't understand this right now, it doesn't matter because it's not related to principle of electrochemical engineering, but is related to the statistical analysis of data. Okay, fine. So, uh, how does a current uh, based method or a Coulomb counting method works for SOC estimation? So this is a flow chart that indicates how, and again to say that this is not the only way in which you can implement the Coulomb counting method or a current based method for estimation of SOC. This is just one implementation, okay, taken from some research article. So how does this method work? It starts, so your whatever is your embedded system, the microprocessor will start this module. The first thing it does is it looks at the identifies the battery serial number, and then it checks the serial number of the battery which it is currently connected to, and sees and compares it with the serial number which is stored in its memory. Okay, so it is asking it is the same battery. Essentially, that question is decided by whether the serial number that the microprocessor reads now is same as what is stored in its memory for the previous time. Okay. If the answer is yes, what it will do is it will read the historic data of the SOC from the memory and will come to this position. Okay. On the other hand, if the battery serial number doesn't match with the what is stored in the memory of the embedded system, then the answer is that it is not the same battery. So of course, it becomes a new battery. If it becomes a new battery, then it will use some method to determine what is the SOC of the system. Remember, it was an old battery, then the SOC was already available. It will make use of it. Okay. If it's a new battery, then it has to use some other method to find out what is the SOC of the cell. And then what it will do is it will set the SOH, the health of the cell, as 100% because it's a new cell. Okay, and then it will set the depth of discharge as 100 minus SOC at this time. T0 is the time that we are talking about. Okay, so eventually, whether the battery is new or battery is old, we come back to this position wherein the system knows what is the SOC at current time. okay, or the previous time instant. And then what it will do is it will monitor the voltage of the battery and the current flowing to or from the battery. So this is VB and IB. The question that it will ask or what will trigger an event in the microprocessor is what is the value of the current? Okay. If the current value is zero, then obviously the battery is at open circuit. So what it will do is it will say that SOC is whatever is the SOC it has um, gotten at this point in the algorithm, and it will just put it back into the memory and indicator if it is required to project to the indicator. Okay, so that's a straightforward thing. The battery is idling. The other situation could be that the current is non-zero and is less than zero. So less than zero is the thing used in this implementation to indicate that the current is being drawn from the battery is discharging. So if the current is less than zero, then what it will check, first thing it will check is whether the voltage of the battery is greater than the minimum cutoff voltage. Okay. If the answer is that the voltage of the battery is not greater than the minimum cutoff voltage, then what it will do is it will cut off the battery from the external circuit because the battery is at fully uh, discharged state. Okay, and then what it will do is it will say that the depth of discharge is SOH of the battery. It's left as an exercise for you to think why the state of health of the battery becomes equal to depth of discharge when the battery is uh, at a voltage which is equal to the minimum cutoff voltage. Okay, so that's left as an exercise for you. If on the other hand, it is the current is flowing from the battery, but and also the voltage of the battery is greater than the minimum cutoff voltage, then what it will do is it will calculate the depth of discharge at time t, that is updated time, from the depth of discharge that it has calculated at the previous time instant, multiplied by the eta times delta DOD. Now, how this delta DOD is calculated? It is calculated similarly using this equation. Okay. Except that this was in terms of SOH. Actually, what you calculate now, you are only calculating the last term in the equation. Okay. So you just calculate, except this plus sign, it will become plus minus will become minus plus because we're doing depth of discharge and not SOC. Okay. So again, we'll not go into question why. It turns out that you are required to perform less number of algebraic operation if you do updation using DOD rather than using SOC. Okay, so it will calculate the change in DOD in this time instant and then also update the SOC, which is SOH minus DOD. Okay, and then it goes back. So finally, it comes back. It goes back to updating the memory where SOC and SOH are being stored. Remember, if it is coming by this path, then SOH is not updated. Okay, it remains same. Only if it is coming via this path, then the SOH is updated. Okay, uh, and then it goes back and comes back to this point, and we will keep looping like that. Okay, so in real time, this is what goes on in your mobile battery indicator or EV scooty or car indicator. Okay. There is a third part to this question of whether the current is positive, negative, or zero. If the current is greater than zero, then the battery is getting charged. So the thing that you have to determine, this logic system has to determine if the battery is fully charged or not. Okay. For determining whether the battery is fully charged, remember it is not a simple question like whether the voltage of battery is greater than we may or not. Okay. Here we have to use some additional logic that the voltage should be equal to the maximum cutoff voltage. And even if it is equal to minimum cutoff voltage, we will see whether the current flowing is less than the threshold which is decided to indicate that the battery is fully charged. So remember that IV curve. Okay, it has to fall down to C25, C30. Okay, so whether the battery is fully charged, the microprocessor will determine based on the logic which is fed. If the answer is yes, that the battery is fully charged, which means that the voltage is at the maximum cutoff voltage, upper cutoff voltage limit, and the current that it can sustain is less than C25 or C30, then it will say that the SOH of the battery is SOC. Just as I said that this is left as an homework exercise for you. Similarly, think about why when the battery is fully charged, SOC is SOH. Okay, and then it will go back here. Update the SOH, update the SOC, and then loop. Okay. On the other hand, if the charging current is flowing and the check for the fully charged condition gives an answer of no, that is the battery is not fully charged, then the depth of discharge is determined by this equation. Okay. Now the depth of discharge is reducing. Therefore, you have minus sign. And then the SOC is updated and we go around looping this. Okay. So any questions on whatever we have discussed till now? Okay, so if there are no questions, then we will finish the discussion on issues with Coulomb counting by uh, just looking at two problems as which are there with this method. One of the problem, as we have already said, is what is the initial SOC? Because this is an updating method. You need to have SOC value for the initial time, and then the method will give you the SOC value at a future time instant. So you have to get the value at initial time. And in Coulomb counting method, what is done is voltage-based method that we discussed first are used to get the initial SOC. Okay. And then whenever there is time to reset the SOC, then again the voltage-based methods will be used to reset the SOC. Why we require to reset the SOC? So the thing which is implicit here, when I say there will be occasions where this method also has to reset SOC, the error in this method will continue to propagate. Okay, which is to say that if you have, let's say, 0.5% error when you do one updation, the error will become greater than zero point 0.5 when you do the second updation. And when you do the third updation, the error will be either equal to or greater than the second updation. So as a result, the error will keep accumulating in this method. Okay. And so after some time, the sufficient amount of error would have accumulated that the method needs to be reset. You have to get the SOC value from some other method. Okay. So again, voltage-based method will be used. Now, in order to understand why this error propagation or error accumulation occurs, we have this table. Okay. So what we have here is time instants, and I've just digitized them to say first time instant, then or zero time instant, then 1, 2, 3, 4. Okay, so that's your first column. Then what is the true SOC of the system? This is a value that we do not know. Okay, but just to explain the concept, so we say that let's say at time t is equal to 0, the true SOC is 50. Then in the first instant of time, remember we are not saying 1 second, 2 second or whatever. The first updation when this method, this Coulomb counting method does first updation, which could be 10 millisecond, which could be 50 milliseconds. We are not going there. Okay. Let's say the SOC drops to 49. And then when we go to the second updation, the second time instant, the SOC drops to 48. So is 50 to begin with, goes to 49, and then goes to 48 in in reality. But these values we do not know. Okay. Then there are SOC estimates that we are actually doing. Okay. So at time t is equal to 0, let's say the method somehow by based method or by some hook and crook is able to get the true value of SOC. At time t is equal to 0, the SOC which is available to method is also 50. So there is no error in the SOC. Okay. And so that is what is meant here, that delta SOC is 0. Error in this step, of course, there's no step here, is not there. And then what is the error which has been accumulated from time t is equal to 0? So that's a dash. Okay, those trivial things. When we go to first instant of time, let's say this delta SOC, that is this calculation that we have done, this is delta SOC, which is eta times integral of Im dt over from t to t plus delta t. Okay, we do that and it is able to calculate this value as 0.9. Instead of 1, it calculates this as 0.9%. So as a result, what will happen is my method will estimate the SOC as 49.1. Okay, the true SOC is 49. Okay, so the delta SOC or the error in the SOC sorry, delta SOC, the change in the SOC that the method get is zero point 0.9. And the error that is introduced in this step in going from time t is equal to 0, so time t is equal to 1, 0.1 percentage error has been introduced. 0.1 percentage of SOC has been introduced as error. And cumulative error is basically keep adding all the errors. So there was no error here, and 0.1% is added in this step. So the total error becomes 0.1 percentage. Okay. When we go to the second, remember we don't know these values because we don't know 49. Therefore, I don't know this number. This is just to explain what is happening. But whatever be the number, that number comes here. Okay. When we go to the next step from 1 to 2, time t is equal to 1 to 2, again, current measurements are done. And again, the delta SOC is estimated as zero point 0.9. Actually, it is minus zero point 0.9. Okay. So what will happen is the method will start with 49.1 as the SOC value at time t is equal to 1, and it will subtract zero point 0.9, which it has calculated in this step. So its estimate of the SOC will be 48.2. Okay. How much error is introduced in this second step? Okay. The actual drop in the SOC is 49 minus 48, which is 1. Okay. The actual drop, the drop that the method has estimated is zero point 0.9. Okay. So the error which has been created or introduced in the second step in this updation from 1 to 2 is 1 minus zero point 0.9, which is zero point 0.1. Okay. So then, but what is the total error? The estimation is 48.2. The true value is 48. So actually we have introduced an error of 0.2 percentage. Okay, where is this 0.2 percentage coming in? 0.1 percentage from this step in going from 1 to 2, and the 0.1 percentage which was introduced in the step 0 to 1 also gets carried over. As you can see, the value is obtained by subtracting from 49.1, not from 49. So this error which was created in this updation 0 to 1 is carried forward or is added to the error which has been introduced in step 2 updation. Okay, so that is why your cumulative error keeps growing. And if you go down similar step and similar kind of inaccuracies are introduced, so you see that the error will keep on growing. Whatever error has been accumulated in the previous steps, they will add on to the error generated in the present step. Okay. And that is what is a problem with this current based method, that there is a cumulative error propagation and which requires that the method requires a resetting, and therefore you have to fall back to some other mechanism for estimating SOC. Okay. But to give you a perspective is that this is still apart. This is true that the method has this deficiency, but at the present time, this is the dominant method used for estimation of SOC for all batteries that you have. Okay, so your mobile battery or EV battery, whatever percentage charge that they show, they are actually calculating it based on this method. And then, of course, this method has voltage-based method, which will come in between at instances, different times to reset the SOC values. Okay. Any questions up to this point of time? Okay, so if there are, this I can skip. Okay. This we will not cover because I think this requires a lot of background. I don't know how many of you have done state space method and have some understanding of signal filtering or estimation, sequential probabilistic estimate. So I'll just outline the method and although it is not part of the course, just for the sake of completion of discussion, we will have it. Okay. So if we go back to these two methods, remember the first method that we covered is voltage-based method, wherein we primarily use and we only use voltage or primarily use voltage. When we use current, it we can't make a proper use of current. For example, if we do here, okay, we're still saddled with the problem of errors coming. So essentially, this is primarily a voltage-based method. Okay. The problem with this is that we don't know the accuracy very correctly, and we also know the uncertainty band associated with the accuracy. Okay. When we come to current-based method, we again primarily are using current measurements to do that. When we are forced to reset or update SOC outside of this method, then we fall back to voltage-based method. But the problem remains that we do not have a good or any estimate of inaccuracy, any good estimate of inaccuracies and uncertainties associated. Okay, so there is other class of method which are called as model-based measurements or method. In this, what happens is that the method not only calculates or estimate the state of charge, but it also has an inbuilt estimator of the inaccuracies which are getting generated. And then it can use those estimate of inaccuracies which are getting generated to self-correct. Okay, so it does not require resetting, certainly not as frequently as the current based method would require. Okay. So there are a lot of methods which are there. The most common method which or most prominent method which may come into practice is what is called as Kalman filter. So if you have heard about Kalman filter, then essentially those methods are also being applied here. The only thing is Kalman filter is applicable for linear system. A battery is a non-linear system. As we have seen, the current voltage relationship is a non-linear relation. So you have to do something to the method. So you either linearize the system around each estimate or you do something. So there are different flavors of method which are available to take care of the fact that the underlying system is non-linear, while the Kalman filter or theory is based on linear system. Okay, so how does this system work? So this system, this is a schematic representation of the entire thing. Okay, so you have a true system and of course the true state. So this is your cell for which you want to estimate the SOC, and there is a model for the system, which is this block. So this would be some equivalent circuit model, let's say one polarization model, which is there. Okay. So then how does the thing work? There's an input to the system, and that input is taken by your model also. Okay. To estimate the changes. Now, what happens is that whatever goes to your model is the measurement that we do. Okay. What actually goes to the system also includes the discharge current, the self-discharge current, the leakage current, the non-linear current component that we talked about earlier. So all of those components are considered as some noises which are exist in the process. And therefore, the true current that goes into the system is whatever goes to the model plus these noise. Okay. And they are assumed to be uh, a white noise, which means that they are assumed to be a normal distribution of noise. Okay, uh, so that is what is going into the system. Okay, so now the my model for the system uses the measured current value to calculate what is the state of charge of the system, and not only it calculates what is the state of charge of the system, based on that state of charge and temperature of the system, it also calculates what is the expected terminal voltage. Okay, so that is what it gives predicted output, which is state of charge as well as what is the voltage that you expect from the system. Okay, from the cell. Okay, and then in the real system, what is happening? There is some current which is going, the system state of charge changes, and we also measure the voltage of the system. Okay, so we measure voltage of the system, and there is a voltage that is calculated by my model. Okay, and then what is done is there is a comparison which is done between what is the voltage measured by my model with what is the voltage which is measured by the sensor. Okay, and I would like this measurement of voltage to be as close to the model predicted value as feasible. I do not want or I do not expect this calculated voltage to be equal to the voltage measured. Why I do not expect? Because there are going to be sensor noise. So when the voltage measurements are being done, again, no sensor will measure it accurately. So there will be sensor noise. Okay, so what is measured as voltage is this one. Okay, the value that is coming out, and we know that the measured value is actually the true voltage plus whatever bias or noise the sensor has. Okay, so therefore I do not expect my calculated value to be equal to the measured value, but I want it to be as close to it as these noises would allow. Okay, so what is meant by that is that again I expect these noise to have a normal distribution. So what I would want, if my method of estimation of SOC is working best, then when I take this difference between the measured voltage and the predicted output voltage, their average should come down to zero. Okay, because if it's a random noise, it follows a normal distribution, the average would be zero. Okay, so that is how this method works. Okay, we are not going to go into the mathematics of it and why it works like that, because then we have to talk about state space method and the sequential probabilistic estimate. If you are interested, these are the two things that you read and you should be able to get that. So I will not go there. As I said, there are different varieties of Kalman filter, which are looking very promising. So something called as extended Kalman filter, something called as unscented Kalman filter. If you are interested, then you can go there. In this course, it will be too much to include all of these things. Okay. The only point here is that compared to the previous two categories of method, this model-based method requires a lot more memory storage as well as power consumption in the microprocessor, which are going to make use of this model to estimate the SOC and the voltage. So because of that, these methods are not really applied in practice. The idea is if we can find some flavor of these methods, which do not require too much of memory or too much of power for their computation, as well as the cost of these processors and memory come down, then they may be used. You have to remember one thing, that finally whatever power or energy is required by these processor is coming from the battery itself. Okay, because this is part of the embedded system. So my method should not be so computationally intensive that in order to calculate the state of charge of the battery, it changes the state of charge of the battery meaningfully, because it is finally using power from the battery itself. So those are considerations which stop this method from being applied in practice in the present day. But there is a good likelihood for them being applied maybe after 5, 7, 10 years. Okay, so they are in active research. Now it is implicit in our discussion that the method self-corrects. So what happens is if it finds voltage that it has estimated is deviating from the measured voltage in ways which are not expected out of normal distribution differences, then the model will use that difference between the predicted and the measured voltage to update the parameters of the model. Okay. So it will update the R0 value or the C1 value or the state of charge in order that it falls, the predicted value and the measured values are within the uh, random noise distribution. So therefore, that brings in the self-correction power of these methods. Okay. So again, why or how that is done can only be shown when we talk about equations. So we are not including them in the course here. Okay. Any questions up to this point of time? Okay. So if there are no questions, then we will consider the last topic of lithium ion cell before we go back to more principle based topics. Now, before I do that, what I will do is or maybe let me cover this and then we will take the attendance. Okay. So lithium ion cell, if you recall, we have done this discussion previously when we talked about the fact that lithium metal represents one of the most attractive carrier of electrochemical energy because its standard electrode potential has the highest magnitude and it is the lightest metal. Okay, so therefore the energy carried per unit weight is the best value. Okay, but if you make a cell with lithium metal as the negative electrode, then you have safety problems which come because of change in electrode shape, dendrite growth, filamentary growth, and thermal runaway. Okay, so because of that, there was this guy Armand who in 1974 proposed that we use only lithium ion. There is no lithium metal inside the cell. And if there's no lithium metal inside the cell, all of those safety related problems, or most of those safety related problems can be avoided. Okay. So how does this cell works? It works by having insertion or intercalation compounds as positive and negative electrodes. Okay. What is the negative electrode that is used? So graphite is an example of a negative electrode. This is a schematic representation of what graphite is. It's basically AB stacked graphene layers, one on top of other. So each layer, the carbon atom is sp2 hybridized and arranged in hexagonal rings, okay, interconnected hexagonal rings, and it forms a sheet. And then you have sheets stacked over one another where they are slightly displaced, and that's the most stable structure. That's basically your graphite. Okay, for our purpose, we will represent graphite as these, each line representing a sheet, collection of line representing a, a graphite particle. Okay, so how does this particle work in a lithium ion cell? Uh, During the charging, lithium ion in the electrolyte will go inside between these two layers. Okay, when it goes inside, it brings in a positive charge, and in order to compensate that positive charge, an electron is taken from external circuit, and that leads to charging. Okay, which is written here that C plus X Li plus, and similar amount of electrons are taken, and the compound that we form we can represent as LiXC. So that is what happens during charging. During discharge, lithium ion will come out, so it will de-intercalate or exert out of the graphite particle. When it goes out, a positive charge goes out from the structure, so an electron will leave, and that will uh, lead to the discharge of the negative. So this is usually negative electrode in lithium ion cell. Okay. How much, where is this charge stored? So this charge is spread over these carbon atom. Okay. One electron is spread over about 24 carbon, about 6 carbon atom. Okay. So that's how the charge is spread. Okay. So electron is not localized over one carbon atom, spreads over 6 carbon atoms. Okay. It could be over 12 or 24 depending, but the maximum, the lowest amount of carbon atom which can accommodate an electron is 6. Okay. How does a lithium ion cell work fully? So this is a schematic representation. Let's say this is graphite electrode, which is negative electrode, and this is positive electrode, which we are saying is lithium cobalt oxide, because that was the first positive electrode used in first lithium ion battery. So reaction could be C plus LiCO2. It's a completely discharged battery. When I charge it, lithium ion comes out from the positive electrode and then goes into the negative electron, and that will cause the current to flow, okay, from the charger to the positive electrode. And you get the negative electrode becomes LiCx, and the positive electrode becomes Li1 minus X COO2. And as we have seen in the previous lecture, the charge is accommodated by sum of the corresponding number of, or X number of, cobalt 3 plus converting to cobalt 4 plus. Okay. So if we look at the first lithium ion cell, they were formed with this. Okay, so negative electrode was uh, graphite, the positive electrode was lithium cobalt oxide. Okay, what is the problem with graphite electrode? The graphite electrode would not survive this uh, going in of the lithium ion and coming out repeatedly. Okay, why it was the problem? The problem was that the electrolyte was propylene carbonate, which I acronym as PC. So when the lithium ion would go inside during charging, the propylene carbonate would also go inside. So not only the lithium ion will go, along with that, some solvent molecule will also go inside the graphene sheet of a graphite particle. Okay. What will happen there is that the electrochemical environment that you have in solution is different from the environment that you have inside the particle. So inside the particle, the environment that is present, the lithium ion can react with carbon and with this solvent, only when the solvent is present, to form some compound. So these three components can react, and therefore they are called as ternary compound. Okay, so that happens during the uh, during the lithium ion insertion. Okay. And when the voltage becomes lower, which is that they will continue. So when you start charging, remember when you start with a discharge battery, the potential of the negative electrode is little higher. Okay. How we have shown there, when we consider the discharge, why we have lower cutoff potential. Okay. So let's say we are there. So remember negative ion potential when the battery is fully discharged, this is the negative electrode potential. As we continue to charge, the potential of the negative electrode falls. Okay. So your in the first generation, when people tried to use graphite as negative electrode, when you charge the battery, these when the lithium ion are going inside, solvent is also going inside, and at the same time, the potential is going down. Okay. When the potential goes down sufficiently, okay. So when they are going inside and the potential is going down, not by very large amount, but some amount, these ternary compounds are formed. And when you take the continue to charge the cell, the negative ion electrode potential continues to go down. When it goes down to sufficiently lower value, uh, these ternary compound decompose. So they form smaller compound, usually some gas component also. And these gases will want to come out because they don't, the earlier the solvent and those things have gone inside because the electron density there could interact favorably with these entities, and therefore there was attractive force. The gases don't interact. Okay. So there was no attractive force, and because of entropy, they would want to come out. And when they want to come out, they will do that in a very vigorous fashion. What that will do is it will displace or etch out the sheets of graphene. Remember these different sheets of graphene that we have here, there is no covalent bond between two sheets. They're held together at their position by van der Waals forces. Okay, the covalent bond is only within a sheet. The two sheets or any two sheets are not connected by a covalent bond. Okay, so when the gas is looking to come out, it is possible for it to displace the uh, a sheet, graphene sheet on one side of it so that it can come out quickly. Because it's like deskinning the graphite particle. You're removing it layer by layer, okay, or several layers at a time. That is what is called as exfoliation or skinning of the graphite sheet. And that is detrimental. So your negative particle is actually breaking down. Okay, it is getting deskinned. Okay. The other problem which was there with this graphite electrode was that inherently the graphite electrode is unstable in this environment. It will react with propylene carbonate. Okay. When it reacts, it will form a layer. So this is the thing that we talked about the situation when the solvent for the solvent which has gone inside and what it is doing. Okay. But these particles are also surrounded by the solvent, okay, because they are immersed in the electrolyte. And at the surface, these propylene carbonate can react with the carbon and form a set of compounds which will deposit over the graphite particle. This is called a surface electrolyte interface. Okay. What happens is during the discharge, this layer grows because during discharge, the lithium ion has to come out, the particle shrinks, and there is crack in this layer. So therefore, more exposed graphite particle will react. And so during the discharge, this will grow, and during the charge particle, it again dissolves. Okay, so this layer is getting formed and then getting dissolved and again getting formed. As a result, new and new. See, otherwise what happens is that you form a layer of this surface electrolyte interface. It will prevent the inside part of the particle from reacting with the solvent because it is now shielded by the surface electrolyte interface. But if this layer grows and dissolves, it will create spaces wherein the particles is now exposed again to the solvent. And then the solvent will react with whatever part is exposed and similarly will continue to do that. As a result, this particle gets eaten up pretty quickly. Yeah, it leads to other problems that we will not talk about in the course here. But this is just to tell you that when people try to use this concept of the battery, okay, negative electrode as graphite, LiCO2 as positive electrode. then these cells were not working. And they were not working because the negative electrode have these problems. Okay. Just look at the timeline. This Armand proposed this in 1974 that let's use lithium ion alone. Okay. Graphite, we know it from a long time. Okay, pencils, the lead which we know were there in 1870s or even 1700s. So this was known much before. Okay, the concept itself came into being in 1974. The positive electrode, this lithium cobalt was developed by a person called Goodenough in 1982. Okay, so basically you had all the pieces which are required to make the battery work by 1982. And from 1982, people tried putting these things together to make a working cell. But because of this problem, they were unable to produce a cell which can work. Okay. The first battery, which was produced by Sony, came out in 1991. Okay, so it took another 9 years for people to figure out how to make a stable system, even when all the components were known. And what did they do? So instead of using graphite, they use a defective carbon, which was called as soft carbon. So what is soft carbon? A pristine graphite will have layers which are stacked in AB-AB fashion, and there is no covalent bond between the layers. Okay. A soft carbon is where you have not graphitized the thing completely. So you will have layer which are not stacked in AB-AB. There will be some, so they are not parallel. There may be some inclination. And some of the layers may also have a covalent bond linking them. Okay, so you can create soft carbon. This is obtained by you starting with a petroleum pitch and heating it at higher temperature, but not going to very high temperature. Graphite requires you to go to 2400 degrees centigrade. Okay, this is done about 1000 degrees or so. Okay, so you get a carbon like this. When you get this defective carbon, what happens is it prevents solvent ingress because there are these barriers. Okay, either there is not enough space because the layer are not oriented parallel, or there are some covalent bond which will stop solvents to go. Okay. So getting a defective material, in some sense, also in many situations is helpful. So because of that, the propylene carbonate could not ingress, and you have less exfoliation of particle, and because of which it is possible to create a commercial battery. Okay, provided an specific energy of 80 watt hour per kg. Okay. Then Sony came up with second generation batteries around 1995. Okay, here what they have done is they use hard carbon. This hard carbon came from starting from coal tar pitch or coal tar instead of petroleum pitch. Hard carbon is even more defected carbon. So layers are even more misoriented, and there are a lot more density of this interlayer bonding, much more than soft carbon. Okay, so because of that, it was possible to for them to accommodate more of lithium ion before solvent will start to ingress, and therefore their amount of lithium that they can accommodate become higher, which means that the batteries uh, charge capacity become higher, and that led to an increase in the specific energy, 120 watt hour per kg. Remember, if you do not remember, just I'll remind you that the specific energy for lead acid battery is just 40 watt hour per kg. Okay, and nickel metal hydride is about 60. Okay, so we're talking about huge jump in the energy. Okay, then came the Sony third generation battery of around 97, 98, where they were able to figure out making use of graphite. So they could get over soft carbon and hard carbon, but go to graphite itself, because what it did was it increased the storage capacity by much higher amount. Okay, it also provided a flatter discharge. I think we can ignore all of this. So it could provide the synthetic graphite that Sony was able to made in 97, 98 could store about 350 milliampere hour equivalent of charge per gram, while the maximum capacity for pristine graphite is about 372. So you're almost very close to the maximum capacity. Okay, and the specific energy for this cell therefore was pretty even higher at 155 watt hour per kg. Remember, we're talking about cell in 1997, 98 would provide you energy of 155 watt hour per kg. The best cell that we have now, after let's say how many about 30 years, is giving us energy of 250 watt hour per kg, 250 to 265. Okay. Uh, how was Sony able to get this graphite work in the battery, which was not possible from 1991 to, let's say, 1996, was that they changed the solvent. Okay, so instead of propylene carbonate, they experimented with similar homologous series compounds such that they do not intercalate, and not only they do not intercalate, co-intercalate, but they also form SEI layer that does not dissolve so rapidly or so much as the SEI layer which is formed with PC. Okay. So what they used was EMC or DEC. Okay. So these are the compounds here. This is just a timeline of how much time it takes for technology to come through. The most common solvent which has been used in lithium-ion cell is ethylene carbonate and ethyl methyl carbonate, okay, in ratio 1:1 or 3:7. But there are other popular combination which are used. Okay, ethyl carbonate is the main component, but the problem with ethyl carbonate is that it is not solid at room temperature. So therefore, you have to mix with either DMC or EMC or DEC in order to ensure that everything becomes a liquid. Okay, so I think that is all that I would cover in today's class. There will not be any class on Thursday. On Monday, you have quizzes in LH 114, and don't log out from the meeting because I'm going to download the attendance. Okay. In the meantime, if there is any query on whatever I have covered today, then you can ask questions now.
So what is syllabus for the quiz?
Syllabus for quiz, as I said, was starting from supercapacitor up to lithium and batteries, or up to whatever I have covered in the uh, till, let's say, the non last two lectures you can leave out. So all that we covered in the online classes, you will not come. So from supercapacitor up to the last class that I took physically. Okay, that will be the portion of the quiz.
Okay, sir.
Any other query? If none, so remember we have quiz on Monday, which is 23rd. And as I said that this time anybody coming with anything to the exam venue will not be allowed to give quiz. You have to come only with pen and calculator, no mobiles, no electronic device, no smartwatches or anything. If anything is found, you again go to disciplinary committee. Okay, you do not have to, I do not want to hear that I brought the bag, I forgot, and I'm switching off. Nothing is allowed inside LHC when you come for the quiz. Okay, so I'll stop here. You can log off from the meeting.